Welcome back for another deep dive. We're going to be looking at, this paper that's been making some noise, scaling transformers for low bitrate, high quality speech coding.
Yeah.
Really interesting stuff. We're talking about speech codecs, those things that power our voice assistants and, increasingly our generative AI models.
Right.
This research is diving into a new way to design these codecs using transformers,
Yeah.
those neural networks that have been really revolutionizing AI.
hmm
And the big question they're asking is, how do we scale these things up to make super high quality codecs that still have a low bitrate?
Yeah, it really flips the traditional approach to codec design on its head.
Right.
Because, typically we've always tried to make codecs as small as possible.
Makes sense, right? You've got limited processing power on devices.
Exactly. Keep that parameter count low.
Oh,
Right. So we've been using architectures like convolutional or recurrent neural networks. They have these really strong inductive biases. But this paper is saying, well, what if bigger is actually better?
mm.
Especially when we're dealing with these massive AI systems
Yeah.
that already have billions of parameters.
So the thinking is, if you're already working with these huge models, a bigger codec isn't going to add that much overhead computationally.
Exactly.
Interesting approach.
Yeah, and by scaling up the codec, they're saying we can actually get better audio quality, A&D, better compression,
Right.
which is especially important for generative models.
Right.
So those models really need detailed audio representations.
So the paper talks about how traditional neural audio codecs, or NACs, as they call them,
Yeah.
have some limitations when you try to use them in these modern AI pipelines. Can you talk a bit more about that?
Sure. So traditional NACs, they're usually based on convolutional or recurrent architectures, and they've really struggled to scale effectively.
Mm.
As you try to make them bigger and more complex, they become really hard to train and optimize. And the paper points this out in section 2. Even with some architectural changes and tweaks, the biggest convolutional-based codecs like Soundstream and encodec,
Yeah.
they barely reach 1 billion parameters.
So are transformers the key here? I mean, they've certainly been able to scale in other areas of AI.
That's exactly what the researchers are exploring.
Okay.
Transformers can handle huge amounts of data. They can find these complex relationships.
Right.
They've been incredibly successful in natural language processing and computer vision.
Yeah.
But as they say in section 1, their use in codecs has been pretty limited.
Okay.
Often they're just used for specific parts, like the bottleneck, like in Mimi.
If transformers are so good at scaling, why haven't they been used more in codec design?
That's a great question. And it all comes down to the technical details of how codecs actually work.
Okay.
Most codecs rely on residual vector quantizers, or RVQs,
Right.
to compress all that information into a smaller number of bits.
Okay.
And while that's great for compression, these RVQs create these really complex streams of tokens. And generative models have a really hard time processing those effectively.
So it's almost like having a powerful engine, but a really bad transmission.
Exactly. You can't use all that power.
Right.
So the researchers saw this as a bottleneck.
Yeah.
And they came up with a solution. Replace those RVQs with Finite Scalar Quantization, or FSQ.
FSQ.
All right?
I like it. Tell me how that solves the problem.
So FSQ is described in section 3.2,
Okay.
and it takes a much simpler approach. Instead of using a predefined codebook like RVQs, FSQ directly quantizes the audio's latent representation.
Right.
You're basically dividing this continuous range of values into discrete levels.
Yeah.
And this gets rid of those complex token streams that RVQs create.
Oh, I see.
It makes the representation much cleaner and easier for generative models to handle.
So it's simpler to encode,
Yeah.
and the output is more AI friendly.
Exactly. And there's another cool thing. It can be decomposed into a residual form post hoc. They talk about this in section 3.2.1.
Post hoc. So you mean you can actually change the quantization after the model's been trained?
Yeah.
You got it.
Wow.
And this gives you so much flexibility. You can adjust the codebook size. You can change the reconstruction quality.
Yeah.
You can even add a residual structure without retraining the model.
So that's a codec that can adapt on the fly.
Yeah, it's a really powerful concept. Opens up a lot of possibilities.
All right, so we've talked about the limits of traditional codecs, the potential of transformers, this new FSQ approach. Now let's get into the architecture. They propose this transformer autoencoder, or TAE.
Yeah, so as you can tell from the name, TAE uses a lot of transformer blocks in both the encoder and the decoder.
Okay.
Each block operates at a specific temporal resolution, and they use these strided convolutions for downsampling in the encoder
Right.
and transposed convolutions for upsampling in the decoder.
They mention this patch-based approach in Section 3.1, inspired by vision transformers. What's that all about?
Oh, it's a cool parallel to how images are processed. Instead of processing the whole audio sequence all at once,
Right.
they break it down into these smaller patches before feeding it to the encoder. So it's like working with smaller pieces of the audio.
Exactly. And this lets the transformer focus on the local structure within each patch, which helps it capture those really fine-grained details.
Makes sense. Now, they also emphasize minimizing temporal resampling within the architecture.
Yeah.
Why is that?
Well, if you do too much resampling, you can lose information,
Oh.
and it creates bottlenecks.
I see.
So by minimizing it, like they explained it in Section 3.1, they keep a high level of detail through the whole encoding and decoding process.
Okay, cool. They also talk about this specific filter bank representation called patch transform or polyphase in Section 3.1. What made them choose this one?
It has some really great properties for perfect reconstruction and error resistance.
Uh-huh.
It means it can accurately recover the original waveform from the encoded representation.
Okay.
And it's really resistant to errors that can happen during quantization. They go into more detail about why they choose it in Appendix B.4.
So it's like a safety net to make sure the audio signal stays intact.
Exactly.
Now, we can't forget about the discriminator network.
Absolutely.
That's a crucial part of any good generative model.
Right. It guides the codec to produce really realistic and high-fidelity audio.
So what kind of discriminator did they use?
They took inspiration from the encodec discriminator, but they made some key changes.
Right.
First, they increased the number of channels to make it more powerful at telling the difference between real and fake audio. That's in Section B.5.
Got it. They also mentioned addressing systematic biases and a late training bias in Section B.5. Can you break those down for us?
Sure. They noticed that the traditional discriminator design had some built-in biases that could lead to artifacts in the generated audio. For example, it was overly sensitive to the noise floor of the signal.
Interesting.
So they made two adjustments. They implemented unevenly spaced STFT resolutions to deal with the systematic biases. And they scaled the magnitude of the complex STFTs to deal with the late training bias towards the noise floor.
So they basically fine-tuned the discriminator to be more picky,
Yeah.
making sure it focused on the parts of the audio that humans actually care about.
Exactly. And all these modifications are detailed in Appendix B.5.
Okay.
They led to a big improvement in the quality of the generated audio.
Now let's talk about the training process. They train the model in 2 stages, right?
That's right. Pre-training and fine-tuning. They outline this in Section 3.4.
Right. So pre-training was all about getting accurate audio reconstruction.
Exactly. They used a combination of reconstruction losses, L1 loss, and STFT loss.
And they gradually phase those losses out as training progresses, right?
Yeah, they use an exponentially decaying weight on those losses, as described in Equation 4. This makes sure they don't interfere with the more nuanced learning that happens during fine-tuning.
All right. So what happens during the fine-tuning stage?
That's where they introduce a perceptual loss based on the pre-trained WaveLM Large model.
Okay.
WaveLM Large is this really powerful, self-supervised speech representation learning model. And by using its knowledge, they can guide the codec to produce audio that not only sounds good objectively,
Right.
but also aligns with how humans actually hear speech.
So they're teaching the codec to think like a human listener.
In a way, yes. By using those sophisticated representations from WaveLM Large,
Yeah.
they can refine the output to make it sound more natural and intelligible.
That's really cool. So what kind of data did they use to train this thing?
They used a mix of LibreLite and the English portion of the multilingual LibreSpeech dataset for training.
Okay.
That's about 105,000 hours of speech data, according to Section 4.
Wow.
And for evaluation, they used the test clean subset of LibreSpeech, which has these really high-quality recordings.
That's a lot of data. And they trained it on 16 H100 GPUs. Must have taken ages.
Oh, it was a huge computational task. 500,000 steps for pre-training, and then another 150,000 for fine-tuning.
Wow.
They used the Atom W optimizer. It's all in Section 4.
Sounds like they really went all out to make sure this model was trained properly.
Absolutely. They were very meticulous about everything from the data they chose to the fine-tuning of the architecture.
Okay, so before we get to the results, I'm curious about how they actually evaluated the model.
They took a very thorough approach. They used both objective and subjective metrics to assess the quality and performance. It's all described in Appendix D.
What were some of the objective metrics they used?
Well, they used several, including SISDR MEL distance, STFT distance, PET, eSQI, STUAY, and MOSNet.
Okay.
SISDR measures how similar the original and reconstructed waveforms are,
Right.
while MEL distance and STFT distance look at the spectral fidelity, making sure the codec keeps those fine-grained frequency characteristics of speech.
But they didn't just rely on the technical measurements, right?
Nope. They did a subjective listening test using the MUSHR format.
Right.
That's a standardized way to evaluate audio quality. 24 participants rated the quality of TA's reconstructed audio compared to the original, so they could get a sense of how humans actually perceive the performance.
Really important to consider the human experience.
Absolutely.
So after all this training and evaluation, how did TAE actually perform?
Well, that's what we'll find out next. They compared it against some of the top codecs out there, and the results are pretty amazing.
All right, let's hear it.
Yeah, they didn't just look at TAE on its own. They compared it to a bunch of other leading codecs. DC, Speech Tokenizer, Semantic Codec, Encodec, and Mimi. They list all those in Appendix C.
So they really put it up against the best of the best.
Right. Like the DAC encodec and semantic codec, those are designed to handle all sorts of audio like music and speech.
Right.
While Mimi is specifically made for streaming.
So T80 had some tough competition.
It did. And the results are in Table 2.
Okay.
They actually looked at two versions of TA, one with a single token per time step and one that used that residual decomposition we talked about earlier.
Right.
And both versions beat the baselines on every single objective metric.
Those were the SISDR, MEL distance, things like that, right?
Yep, all those. SISDR, MEL distance, STFT distance, POSQ, STOIY, and MOSNet.
Okay.
And in all of those, a higher score means better performance.
Yeah.
And TAE consistently came out on top.
So it wasn't just a little bit better, it was significantly better.
Exactly. And what's really impressive is that it did all that while keeping a really low bit rate and tokens per second.
So it's not just about quality, but also about efficiency.
Absolutely. TAE manages to find this great balance between high quality and low bit rate.
Really shows how well this approach works.
It does.
Now, what about that subjective listening test? I'm curious to hear how people actually rated the audio quality.
So Figure 2 shows the results from the MUSHRA listening test.
Okay.
They had people listen to the reconstructions and compare them to the original audio, and TAE got state-of-the-art results. It was way better than all the other codecs.
Oh, how much better was it?
Well, TAE's scores were super close to the ground truth,
Really?
which means that listeners could barely tell the difference between the original and the reconstruction.
That's incredible. It sounds like they've really pushed the limits of what's possible with speech coding.
They really have, and there's more. The appendix has some extra findings and explorations.
Oh, yeah. What else did they look into?
Well, they did some experiments on model scaling. They talk about that in Appendix 8.2.
Okay.
As you might expect, the bigger models did better.
Yeah.
But even the smaller TAE versions had really impressive results.
So there's potential to make this model even better.
Oh, definitely. They also looked at ways to get higher compression rates by changing the encoder and decoder. They described that in Appendix A.3.
Right.
Of course, when you push the bit rate lower, the quality drops a little bit.
Makes sense.
But it shows how flexible their approach is.
Yeah. Did they think about using this for streaming applications?
They did. They created a causal variant of TAE specifically for streaming.
Oh, wow.
And the results were really promising. They're all in Appendix A.4.
Did they only test TAE with English speech?
You know, that's interesting. They actually tested how well it generalized to other languages,
Really?
even though they only trained it on English data. And Appendix 8.5 shows that it performed just as well or even better than codecs that were trained on multiple languages.
That's amazing.
Yeah.
It really speaks to the power of transformers to learn these generalizable representations.
It does. They also explored how TAE handles audio of different lengths in Appendix A.6.
Okay.
It was able to deal with a wide range of lengths, even ones that were longer than what it was trained on.
So it's pretty adaptable.
Yeah. It seems like they've really thought of everything.
They have. They even looked at how efficiently the codebook is used.
Yeah, that's in Appendix A.8.
Okay.
TAE achieved almost perfect utilization.
Wow.
Which means it's squeezing every bit of information it can out of the codebook.
So how did TAE do in terms of real-time performance compared to other codecs?
They looked into that too. It's all in Appendix 8.9.
Yeah.
And despite being so big, TAE was still competitive when it came to processing speed.
They really did a thorough analysis. Now, the paper did mention some limitations. What were those?
The main limitations have to do with the training data.
Go.
They acknowledge that training on a bigger and more diverse data set with different languages, accents, and acoustic environments could make it even better.
So there's still room for improvement.
Oh, yeah. And they also point this out in Section 5. They talk about the model's size being a potential issue.
Right, it has a lot of parameters.
Yeah. And while that leads to great performance, it also means it needs a lot of computing power, which might be a problem for some applications. They discuss this in Section 5.
Makes sense.
Yeah.
Well, this has been a really fascinating look into speech coding.
Hmm.
I'm blown away by how innovative this research is. It really is impressive work. It makes you wonder what the future holds for this kind of technology.
Yeah, it's exciting to think about the possibilities.
Well, this has been a fantastic deep dive into the world of speech coding. I've learned so much.
Me too. It's been great discussing this with you.
And to all our listeners out there, thanks for joining us on this journey.
Yeah, thanks for listening. Keep exploring and curious.